Welcome folks to another physics lesson, and this time we're going to focus on something which is called the work energy theorem. So hopefully we're going to do a little bit of work, and we're going to do that by using up some energy. So if we can just do a little bit of a backward recap. So far, hopefully you understand that there's a relationship between work and force, these concepts here, and force needs to be done on an object to do work, and work is a measurement, I guess, of when force is being done to move that object a distance. And today what we're going to focus on is we're going to join up these concepts of energy and work and try and put a little bit more detail on that. Okay, so what are we looking at here in terms of energy? Well, sometimes we see this quote here, and it says quite simply that energy is the ability to do work. And I like to put it more so as that energy is required for work. In other words, you need energy to do work. So there's that relationship between those two. And also conversely, when work is done on an object, the energy is changed. Energy can be increased or decreased. So that's another way to look at that relationship. Okay, so let's look at two examples here. The first one we're going to look at is we're going to look at an example of where there is positive work. So we're just going to draw that in. Normally positive things are green, right? So we're going to draw that in with our little green. So when we're talking about positive work here, well, that's when energy is added to a system. So if we take the example in the diagram, I've just drawn a person lifting a ball. When you lift the ball higher into the air, you actually do work on that system of the green ball there. Because there is an increase in the potential energy of the ball as it moved through that zone. So as the ball moved upwards, it gained height. Now it started from a position of h equals 0, which we sometimes call the reference point, and it gained potential energy. So it gained energy. And that is called, or we state that is positive work because energy was added to the system. So if we look at an example on the other side of things where negative work is done, so we're going to have to put in, normally our negative is red, so let's put that in. Energy is removed from the system when negative work is done. So energy, if you like, flows from that system. So energy, if we look at a little bobsleigh, we'll use the bobsleigh as an example, and energy is removed from that system when friction causes it to stop. So if we look at the bobsleigh here, it's moving. They're moving nice and quick. The person at the front has got his head down, his or her head down. Why, I do not know. I guess aerodynamics, physics, and all that. And the bobsleigh comes in, and then the friction causes it to come to a stop. So there's friction acting upon it that's causing it to slow down. And we might show the friction in terms of the forces acting against it, which causes it to stop just before it hits this area here, hits the flag. So that's a good thing. And so that's an example of negative work where energy is removed from the system. And that's normally when the force is opposite to the motion of the object or slowing the object down. So at this point, we probably should talk about what mechanical energy is. Well, mechanical energy in physics is a term used to describe the sum of potential and kinetic energies. And it's a macroscopic energy associated with a system. So when a system is able to move, there is mechanical energy. And mechanical energy is the ability to do work. And this is sometimes seen as the total energy in many systems. And we have a couple of examples here. This would be an example, the rock on the cliff of potential energy, and molecules moving around would be a good example of kinetic energy. So these two, potential energy and kinetic energy combined, would give us mechanical energy. So it's a total energy of a system. And there's many examples in real life of energy, of mechanical energy doing work. For example, this wrecking ball that I've drawn here, has the ability, when the ball swings, it has the ability to do some work, to bash into things, knock things down. So do all of these, mechanical machines or levers there. So levers, inclined planes, screws, hammers, so on. These are examples of, where there's mechanical energy doing work and getting something moving. So let's talk about what those energies are. Kinetic energy is the energy associated with things that are moving. So if there's a very tidy equation in physics for kinetic energy in classical physics, and that says that kinetic energy is equal to half mv squared. Now there is a more complicated version of that for objects moving at high speeds, high speeds relative to the speed of light. And that is more covered in Einsteinian physics. But in the classical realm, it is a simple equation, a half mv squared. So if we look at an example here, and in our example, the bowling ball is moving in, it's thundering in. Of course, it's going to hit these pins. It's going to do mechanical energy knock. It's going to set them in motion. So if we look at the bowling ball here, it's going to move. It's got, let's say, a mass of 5 kilograms, and it's got a velocity of 10 meters per second. So in our example here, the kinetic energy would be a half times mv squared. So this squared is going to be 100. So it's going to be 100 multiplied by 5, which is 500, multiplied by a half, which is 250 joules. So energies are the unit for energy, SI unit, is joules. So the kinetic energy of that system, of the bowling ball, will be 250 joules. So we should also highlight at this point that kinetic energy is proportional not to V. It's not a direct proportional, but to V squared. And hopefully you can see, if we look at the red line here, that's the Einsteinian world. But if we look at the green line on our graph, it shows us that sort of exponential curve that we would associate with such a proportion. So velocity has a major impact on kinetic energy, more so than mass, is what this is telling us. Quick example of kinetic energy. A bird of mass 2 kilograms is traveling at a speed. What is its kinetic energy? If the speed of the bird doubles, what happens to the kinetic energy? Maybe you can pause the video and just see if you can answer those questions, and then I will do them. Okay, so let's have a look at both of those. A bird of mass is moving. We have the mass, we have the velocity. So we're in good shape to answer that question. We just simply plug in those numbers and we get 36 joules. For part B, it is very important that we go back to that it's not a proportional, the kinetic energy is not directly proportional to velocity. And so if we wanted to figure out, how would KE2 relate to KE1? Well, we're just going to put in that the velocity was doubled, so 2 times V1. And we're going to try and write KE2 in terms of KE1, and we're just going to use green for that. So we're just going to multiply that out, and we would get 4 times V1 squared. Now, if we actually factor out this 4 and we bring it to the front, we will get 4 multiplied by a half mv1 squared. And so what we see is that that is equal to 4 times KE1. So if the velocity is doubled, the kinetic energy is multiplied by a factor of 4. 2 concept questions for you to ponder here. Can kinetic energy be negative? And also, how does a car's kinetic energy increase as the car starts moving? We have some movement here and the car starts moving to the right. How does its kinetic energy increase? Just pause the video and have a think about that, please. Well, the answer to the first one is that no, kinetic energy cannot be negative. It is purely positive, because we have a velocity. Even if it's a negative velocity, it's going to be squared, which is going to give you a positive anyway. And how does a car's kinetic energy increase? Well, the reason for that, if we view the car as being the system here, is that there is work done on the system. And that work done on the system, what that does is it raises the energy of the system. So the work, in fact, leads to a change in energy. And that change in energy is positive, and there is kinetic energy gain by the system. So positive work is done to the system, on the system, and it raises the energy. So what is potential energy, I hear you ask, and what is that handy little formula that we use to describe potential energy? Well, potential energy is the energy, the potential amount of energy that a system has relative to a base level, a reference base level. Now, there is different types of potential energy. So what we're going to focus on right now is gravitational potential energy. Of course, there's chemical potential energy in a battery. There could be elastic potential energy, but we're just going to focus on gravitational potential energy. And if we look at this little diagram that we've done, of course, that energy is, the unit for that is a joule. If we look at the diagram that we've done, this rock here, relative to the water, actually has some potential energy. And the reason why the rock on the edge, perilously close to the edge of the cliff, has potential energy is because it can be transferred into kinetic energy. So it has some stored energy there. We can capture the value for that potential energy by merely looking at the mass of the object, the acceleration due to gravity, which is a fixed number, 9.81 meters per second squared, and its height relative to that reference point. So, you know, its height in here might be, let's say, 5 meters. And so you would put that in to find its potential energy in joules. So we finally got to it, the work energy theorem. And the work energy theorem, put simply, relates work to energy, to the change in energy. And we already know that work is equal to F delta D. Well, this is another way of looking at it, and it says that work is equal to a change in energy. The net work done on an object is equal to a change in its kinetic energy or potential. And so it all seems very neat and tidy, but I hear you saying, well, Mr. McCormick, I'm going to need a little bit more than that. So maybe you've decided that quite simply you need some more. Well, let's write that in just to make sure that your feelings are heard and understood. You need more. Okay, so we're going to do an example of a derivation here, and hopefully that will help you to understand what's going on. We're just going to get rid of that. So the final point we'd like to get to here is work is equal to a change in kinetic energy. So let's see if we can do that. We begin and we say that work is equal to F delta D, and we know that this F net is equal to MA. So we can substitute that fact in here, and we can say W is equal to MA delta D. Now we also know from kinematics that A is equal to VF squared minus VI squared over 2 delta D. So we can go ahead and put that in instead of A. So we can put VF squared minus VI squared over 2 delta D. Okay, and we also need to put in that the work was equal to M times A times delta D. So the keen-eyed amongst you might already see something that makes our life a little bit easy here. The delta D is going to cancel out. And so what that leaves you with is it leaves you essentially with, I'm just going to pull it out here, work is equal to a half mVF squared minus a half mVI squared. Now this is the same as saying KEF minus KEI. So that is a derivation just showing that the work is equal to the change in energy. Let's look at two quick examples here. If Katniss Everdeen, her of Hunger Games fame, applies a 15 newtons force to pull her bow back by 25 centimeters, with what speed will her 0.15 kilogram arrow leave the bow? So what we're getting here is 7.1 meters per second. You can stop the video and see if you can get that answer, and then I'm going to work it out. So we have Kate over here, and what we're going to do is we're going to apply what we've just learned, which is that work is equal to change in energy here. If you might find it a little bit more difficult to answer this. You can probably do it other ways, but we know that W is equal to F delta D. But a fast way to do this is to assume that the work done on the bowstring gets transferred to the arrow. And so this work on the bow gets turned into kinetic energy. We're assuming that that's 100% efficient. And so we know that the work is equal to change in energy. And we have a statement for work, which is F delta D cos theta. So we can multiply those values for F, for delta D, making sure that stuff like delta D is in meters, not centimeters. And we're also assuming that Kate pulls back perfectly horizontally here, and that all of that force goes into moving the string, and we get 3.75 newtons. Now, if we set that equal to the change in energy, well, the bow actually, the arrow rather, started with a kinetic energy of 0, so did the bowstring before it was pulled back. And so if we just focus on the kinetic energy 2, we can isolate for V. So if we multiply 2 times 3.75, we're going to get 7.5. And then if we divide by m and take the square root, we should, by isolating, get 7.1 meters per second. I've just put another example on the board. This time it is using gravitational potential energy rather than kinetic energy. And just remember a couple of things if you wanted to figure this out. If we want to get the work done here, we could say W is equal to the change in potential energy. And of course, you can get the change in potential energy by looking at mg delta H, or potential energy 2 minus potential energy 1. When you look at that, hopefully you'll get 800 joules. In order to figure out what is the speed, we can assume that work done was transferred into velocity, and we can solve as we did for the previous one. Another type of question you might be asked: a flower pot of mass 5 kilograms is located a certain amount above the ground. What's the potential energy with respect to the ground? Well, that is just mg delta H, or mgh. With respect to the ground, the H would be 15 meters above the ground if ground is reference 0. And what work, so that would actually give us an answer of 750 when we multiply those together, and remember the units are joules. And what work was done to raise it to its position? So to raise it, we added energy to the system, and remember that work is equal to the change in energy. And so if we want to figure out what that work value is, well, it started with an energy of 0, and it got a new potential energy of 750 joules. So the work here that was done on it is 750 joules. One final teaser on a screen there for you to ponder. Put what we've learned into practice. Hopefully you folks are more familiar with the concept of work energy theorem than you were when you started the video. And if you liked the video, then just give us a wee thumbs up, please.